Yes, so thank you very much for the invitation. As far I understood, I have something like 1 hour to talk about it.
Andreas, just one. Okay, so good afternoon and welcome everybody to the penultimate session of this ICTS activity. We had 10 days of school on flavor physics with 8 lecture courses, followed by this 3-day topical conference. So now during these lectures and also during the talks, we have heard about various anomalies that have been around for last few years. And we are very happy to have none other than Andreas Crivellin, who has worked on each of these anomalies in great detail, whether it is touching upon some very cute ideas to explain the anomalies or doing detailed analysis of the anomalies and related predictions. So we are very happy to have Andreas from Paul Scherrer Institute. So without any further delay, let me invite Andreas for his talk. Andreas will take us through theoretical explanations of the anomalies. Andreas, over to you.
Thank you very much for the invitation. As I said, please interrupt me at any time to ask questions. I'm very happy to answer them. Please let me know if I'm going too fast or too slow. So I prepared the talk for around 50 minutes, so there should be plenty of time for explanations, especially because I think at the beginning I can be quick because you already heard about the anomalies. So my main focus should be on the theoretical explanations of them. However, I think it's very important to review them first again. I'm not sure if you heard about all of them, and the nice thing is, except for the last part here, electroweak fit, W mass, and ZBB, they obviously belong to a common pattern, namely the pattern of lepton flavor universality violation. So some new physics that couples differently to electrons, muons, and tau lepton. The electroweak fit, of course, could also be related. Z2BB might be, of course, related to the B anomalies. That's a little bit distinct, but after this new CDF measurement, I find it quite interesting to include this here as well. Then I want to talk about explaining the anomalies. So my main job, I will go through them one by one. And then at the very end, depending on how much time I have, I will present you some selected common explanation. Okay, let's start again with the introduction. I think this is all clear to you, you knew it, but just keep in mind, this slide tells you, we know that physics beyond the standard model must exist. And it's even not small. We can only account for the content of 5% of our universe. 95% are unknown. So then there must be new physics. Also because neutrinos are not exactly massless, and we have a matter-antimatter symmetry. So what you usually do is you extend the standard model. But the problem is you can extend it in many ways to account for these observations, and nothing tells you that the new physics scale to do this will be reachable at future colliders. For example, for neutrinos, you can account them for the masses with right-handed neutrinos from the KeV to the gut scale at 10 to the 14 or 15 GeV. So this doesn't guarantee you discovery. So as I said, the standard model must be extended, but what is the underlying fundamental theory? And can we observe this theory at current or realistic future colliders? And now this is where the flavor anomalies come into the game. So this I subsume here in the intensity frontier in the flavor balance. But what I think is also important that we as flavor physicists also communicate to the rest of the particle physics community that discovering the flavor anomalies or establishing them is not only good for flavor, it's also good for the cosmic frontier and for the energy frontier because we are complementary. So if one sector finds anomaly, the other ones are needed to confirm it, or can it at least it helps to investigate it further. So for example, say we find a new particle at the LHC, then we need flavor to decoupling to determine coupling to quarks and lepton. Okay, Also, very trivial slide, but again, I think it's important to keep in mind. If experiment and standard model don't agree, and we are sure that the experiment was done correctly and the standard model prediction is sound, then there must be new physics. It's the logic from Sherlock Holmes. If you excluded everything impossible, the remaining possibility, no matter how improbable, must be the correct one. So translated to physics, this means no matter how intricate or unnatural the new physics model that explains the anomalies is, if there is really an anomaly, there must be new physics. And what should give us some confidence in these anomalies is that, first of all, you can test higher scales with flavor observables than you can test directly at the LHC. This you see on the plot on the right-hand side. And I think within the last 5 decades, we always observed new physics first indirectly before finding new particles directly. Think about Fermi interaction with the W boson. Think about the Higgs mass from the electroweak precision fit, or think about the top mass from kaon mixing. So it always happened, we had indirect hints, and later the particle was found at a collider. So the hope is history repeats itself. We now see first hints for new physics in flavor observables, and then later this will be confirmed by a direct discovery. Okay, this brings me to the end of the introduction. Now let me start with the overview on the anomalies. Unless there are already some questions, I'm very happy to answer any question here. Okay, let's continue with the overview on the anomalies. The first class of processes, which you are probably very familiar with, is B to S mu plus mu minus process. So what I want to say here is, because it's again important, this is a flavor changing neutral current, so it's very suppressed in the standard model and therefore very sensitive to new physics. That's the first point. The second point is it's governed by a very small set of Wilson coefficients. So by a very small set of effective interactions. Now, these effective interactions are obtained by calculating diagrams like this, just much more complicated because you add gluon or electroweak loops, and this calculation is known very precisely. And the point why you can study these effective interactions is that the particles in the loop are much heavier than the particles outside. So you can contract the loop to a point, and you can just parameterize this effective interaction strength in terms of this Wilson coefficient. And now, as I said, there's really only very limited set of Wilson coefficients which describe any B to S mu mu process. So any observable that contains the B to S mu mu process is described by the same Wilson coefficient. The only differences come from kinematics and phase space. But of course, depending on the process, you also need different input like form factors or decay constants. So calculating the process itself is at the moment the difficult part. The effective interactions within the standard model are very well known. This is not the main source of the uncertainty. So at the moment, what counts is calculating these processes precisely. So we need form factors, we need non-factorizable corrections, and so on. Here we have several observables which contain this B to S mu plus mu minus process, which deviate from the standard model prediction. B sub S to mu mu is great because it's theoretically very clean, but for the experimentalists among you, you know it's very difficult to measure it because it's so strongly suppressed by the chirality of the muons, because you need them back to back. So you have only branching ratios of 10 to the minus 9. So it's statistically limited, but if you look at the CMS, LHCb, and Atlas measurements, you see they somehow lie 20% below the standard model prediction. B sub S to phi mu is SS bar bound state, you have something similar. So again, you see this is a B to S mu plus mu minus transition. Now here, This is theoretically more difficult to calculate because you have a meson in the initial and a meson in the final state. So you need a form factor to calculate this branching ratio as a function of the well-known Wilson coefficient. And this form factor depends on the invariant mass q squared of the lepton pair. Now, you can calculate this with non-perturbative methods like line code sum rules or lattice QCD, and one works for high q squared, one for low q squared, so you can interpolate between them. And then what you see is that the measurement, the crosses, are consistently below the standard model predictions, namely the boxes. So again, there's some deficit. Then there's the famous P5 prime anomaly. This is here. This has the advantage compared to P sub S to phi mu mu that you reduce the dependence on the form factors by choosing these angular observables in a clever way. And then this product you have seen many times, focus on the black crosses from LHC B. You see they lie closer to zero than the standard model boxes. So again, this points toward destructive nuisance.
Andreas,
now,
can I ask a question?
So far, okay. Please go ahead. Thanks a lot.
Yeah. So it's like a very poor experimentalist like me. I was wondering, like, when the theorist colleague, I mean, there's two groups have this error, and thankfully there is a overlapping region. But is there a kind of work towards some sort of common framework or something like? Can we have understanding of the common theoretical uncertainty, or that's very tough to arrive?
I mean, it's very good that there are two different sets of theory predictions because they use different form factors.
I see. So this is on the form factor side. Okay.
Exactly. This is on the form factor side. So,
but if they have, if they interchange, I mean, has there been? I mean, I want to see on the formulation. So let's say, sometimes you can interchange the form. I mean, what one group is using versus the other. I mean, do they reproduce each other? I mean, sorry if I.
Yes, I mean, the formulas otherwise are identical. The difference is only how you treat these hadronic uncertainties. But I mean, everyone agrees on how P5 prime is expressed in terms of the Wilson coefficient.
Okay.
This is not a problem. It only concerns how you incorporate these form factors and this hadronic correction. And so it's very good that there are two independent calculations with different form factors and different approaches to treat the hadronic corrections, because as you see, they overlap. So this gives us confidence in the standard model prediction.
Okay, please proceed.
Can I just ask some?
Thanks a lot for the question.
Can I just ask one small thing? Why isn't there a theory prediction in
the... Yes, but please speak up. You are very soft.
Okay, sorry. So why is there no theory prediction between the two resonance regions in the Q-square bin in between Jepsa and
because it's very hard to calculate it. Yeah.
Okay.
It's hard to impossible to calculate. I mean, maybe in the future we could do it, but yeah, it's not easy to calculate it there because you don't know how far these resonances are leaking in between.
Okay, thank you.
And then the other point is the form factors. So you can only calculate the form factors at high and low Q squared, and then you have to interpolate, and this also gives you an additional error.
Thanks.
More questions? Okay, good. Then now you might have said, okay, maybe these are underestimated hadronic uncertainties. Maybe this in B sub S to phi mu mu are two small errors in form factors, and maybe B sub S to mu mu is a statistical fluctuation. But now there comes the great thing, namely this RK and RK star. And here we know the theory is not the problem. You can completely neglect the muon and the electron mass, and then the form factors cancel, and your prediction is in principle just 1. But what LHCb finds somehow is something, again, 20% below the standard model. Not only in RK star, but also in RK. And here in RK, this they provided for the first time evidence for lepton-flavor universality violation in a single observable. Now, you can combine everything. I guess you heard about this as well. The important thing again to keep in mind is, first of all these measurements are consistent. You can find some patterns where you change these effective interactions with respect to the standard model that explain all anomalies while not messing up other data. And this is not granted at all. So for example, think about the difference between VCB from inclusive and exclusive determination. Here you can show model independently, you cannot explain it by new physics. But in beta SLL data, it's exactly the opposite. Very simple patterns work nicely. And the pattern I chose here is that you have a left-handed quark current and a left-handed muon coupling, only a left-handed muon coupling here. And here you have a left-handed quark coupling and a vectorial muon coupling, identical for electrons and muons. The reason why I chose this scenario is that it's the one which gives slightly the best fit among all scenarios, more than 7 sigma better than the standard model, and for later purposes, because this is the scenario you get in with the party-salam lepton quark. There you introduce at tree level this left-handed muon current, and at the loop level this lepton flavor universal contribution to C9 via an off-shell photon pancreas. Okay, next anomaly, B to C tau nu. So this is something completely different. This is tree level in the standard model. Not suppressed at all. In fact, the BDKs with the highest branching ratios among all. So in principle, not the place where you expect new physics. Furthermore, for light leptons, you extract the CKM elements from these processes. You extract VCB from here. And there you find a nice agreement with the indirect determination of delta F equals 2 process. So with light leptons, there might be some new physics with muons. I come to this later, but with heavy leptons, there seems to be that against these expectations, there is some new physics. So this plot you know as well, now it's reversed. The cross is the standard model prediction. The circle are the measurements. They lie consistently above the standard model prediction. The standard model prediction is good, but not perfect, because you cannot neglect the tau mass compared to the B mass. So there is some remnant of the uncertainties on the form factor. And it's supported by this measurement of R shape size. Okay, another anomaly, which is quite significant, but somehow not very well known, so definitely something for Belle people, is this delta AFB. So this is the difference between the angular observables in B to D star mu nu minus B to D star E nu. And here, this analysis of Danny van Dijk et al., they found a 4 sigma deviation from the standard model prediction, which is just to a good approximation again 0, because muon and electron mass you can neglect. And then you see here, even assuming very conservative anti-correlation between the errors, you get something like you get more than a 4 sigma preference for delta AFB. Now, what's important about this delta AFB is it's asymmetry. So you need interfering amplitudes to generate this asymmetry, meaning you need scalar or tensor operators. And now you can already see that there could be some nice correlations with G-2 and BS mu mu. I will come to this later. So it is a charge current like B to C tau nu. It involves muons like B to S mu mu and G-2, and you need scalar or tensor operator, so something chirality flipping again like G-2. So I think this anomaly, even though not very well known, is definitely something one should keep in mind for the future.
Can I ask a question here?
Next anomaly.
Sorry,
yes,
Andreas. Yeah, if you just go back to the slide. Yeah, so
no need to be sorry at all. I'm very happy for any question.
So this is a case where lepton universality has been very well checked between the semi-leptonic decays, right? So whatever's causing this is only messing with the differential distribution. So does that help you in some way in terms of building the model, that it restricts what's possible in terms that you know that it's only affecting?
It restricts very much what is possible. So in fact, the only possibility is the scalar leptoquark SU2 singlet. That's the only way you can do it. And then if you look at this left-handed plot, you see exactly what you said. So this boomerang here, this is the constraint, because we know that VCB from muons versus VCB from electrons is to good approximation the same. This is this orange boomerang.
Okay. So sorry.
This is exactly what you said.
So this was a spoiler for something you're going to say later.
It's perfectly fine. I can also explain.
Okay.
It's perfectly fine. I can also explain it here. So you see this boomerang, this is the constraint you mentioned. And the blue region is what you would like to have from delta AFB. And the green regions are the constraints from other angular observables. So you cannot fully account for delta AFB, but you can partially account for it. And you still improve by more than 3 sigma over the standard model hypothesis.
Okay. Thank you very much. Thank you.
Hello. I didn't realize people were asking questions in the middle. So may I ask a question?
Yeah, please.
Can you please go to your slide 16? I was keeping to ask in the end, but yeah, actually one more before, slide 15. Yeah, here. Now, I just wanted, I mean, you have shown us the data, but what is your feeling that Belle 19 is now, somehow so much closer to the standard model? In some sense, I just wanted your feeling.
On the one side, yeah. So it's a little bit. So first, I was disappointed about the measurement because it's significant disagree. But on the other hand, the Barbar 12 measurement was so high that it was nearly unexplainable by new physics. So from that point of view, I was not unhappy that the significance decreased and the central value decreased. And you should also take into account data doesn't age in that sense. So it could have been also the other way around, that Belle first announced their result and then later Barbar.
Yeah, I understand that. I mean, I'm just kind of thinking, because these are, if one is going to say that these are fluctuations, So
sure, it's possible. I mean, that's what statistics
I just
tells
wanted
us.
your opinion as somebody who's been following these things, more or less as an outsider, whether I should now take RD star seriously or not as a outsider.
And if I can interject, what Rohini is asking, can we have a world average excluding Barber 1, 2? If we have
that may be the way.
Sorry, I mean, if I want to be a little bit politically incorrect, that if we take out that Barber 1, 2, and then we have world average, how will this discrepancy with standard model will be? I mean, of course, we don't want to be, exclusive of something or including, but if we do.
You asked my question.
I think it would be something,
but that's really what I wanted to know.
Yes, if you take Barbar out, you are something above 2 sigma.
Okay, thanks. Thank you.
But yes, but I don't think there's a reason to believe that Barbar is wrong.
No, we're not saying that.
You already
I am not really saying that. I think I'm just trying to understand an assessment. I mean, the way, I just go back to 750 GeV, and I know that we foresaw a 3 sigma signal, and then the next result didn't confirm it with higher luminosity. Now, that is the kind of thinking that I have at the back of my mind, and that's the only reason I asked this question.
So my personal opinion is that, of course, if you look at the sigmas, RD star is by far not as convincing as B2S mu. That's clear.
Okay, thanks.
I mean, 3.4 sigma compared to 7, that's not that much. And we know that tau leptons are difficult. What I like about RD star, I will come about this later, is that you can make even model independent connections to B2S mu. This somehow gives me a bit more confidence in RD star than if the anomaly were just there without anything else.
Okay, thank you. That is very useful to know. Thank you very much.
Okay, thanks a lot for the question. Any more? Okay, then let's come to the anomalous magnetic moment of the muon, our next anomaly. Here, if you trust in the theory prediction from the white paper, you have 4.2 sigma. The problem is the diagram here on the right, this hadronic vacuum polarization, where you have pions and so on in the loop. This is hard to calculate. This is what's causing this discussion with the BMW collaboration. But as I said, if you trust the theory white paper consensus, you have a 4 sigma deviation, and it's of the order of the electroweak diagram, so of the Z and W diagrams, if you can see my cursor. Now, this is not small. So if you want new physics at the TeV scale, you already lose a factor 100. So you lose mW squared over 1 TeV squared. So with 1 TeV new physics, you can only explain it if you find an enhancement mechanism. And fortunately, this exists for the anomalous magnetic moment of the muon, namely chiral enhancement, because the anomalous magnetic moment of the muon connects a left-handed with a right-handed muon. This chirality flip is done by the muon mass in the standard model, but in new physics, you can have order 1 Yukawa coupling, so you can compensate for this. What one should also keep in mind is that the anomalous magnetic moment of the muon is a measure of lepton flavor universality violation because of 2 reasons. First of all, if new physics were completely flavor blind, like the photon here, like the Schwinger term, you would overshoot the anomalous magnetic moment of the electrons by orders of magnitude before explaining the one of the muons. And if you have heavy new physics like W and Z, the effect vanishes for vanishing muon mass. So in the limit of lepton flavor universality. So you can consider the anomalous magnetic moment of the muon as a measure of lepton flavor universality, like RD, RD star, RK, RK star. Next anomaly, non-resonant dilepton. Here, what CMS did is they looked at very high energetic electrons above a invariant mass of 1.8 TeV, and they found 44 events compared to 29, plus minus 3.6 events expected. Also, Atlas and Hera had slightly more electrons than expected. Now, if you look at this curve, you can see here, so with some constructive new physics effect, you can do it. So this is the ratio of muons over electrons, and this time electrons have to be higher than muons. And then you see there's some preference for more electrons than expected in this high energetic tails. So these are non-resonant searches. This is for new physics, which is too heavy to be produced directly at the LHC. The next anomaly is the Cabibbo angle anomaly. So here, what you can do is you can use beta, kaon, and tau decays to test CKM unitarity. So you know the CKM matrix is unitary. So the sum of the squares of each element of a row or a column in the CKM matrix must give unity in the standard model. But here you see that first row and first column, you observe a deficit in CKM unitarity. Now, VUD is by far the largest element in this unitarity relation. So you can expect that if this is due to new physics, it should be related to beta decay, because beta decays determine you VUD. Now, the important thing is that in order to determine VUD from beta decays, you need the Fermi constant as input. The Fermi constant is usually measured from muon decay. It's, as you see here, extremely precisely measured, but a single precise measurement of a single observable can never tell you how much new physics there is inside. You always need a second best determination of the Fermi constant. And this you can then reverse by doing it here from CKM unitarity, or you can also look at electroweak fit, and you see there's some tension in between here. Now, I will come to this also again later, but so the CKM Cabibbo angle anomaly can be interpreted at 3 non-exclusive ways, namely new physics in radioactive beta decays, new physics in the determination of the Fermi constant from muon decays, or new physics in a W mu nu coupling, entering again muon decay, which is then a sign of lepton-flavor universality violation again. Then finally, W mass and set to BB bar. So with this new CDF measurement, there's a 3.7 sigma tension in the W mass using a conservative error combination, both for the measurements as well as for the standard model prediction. If you are less conservative, you can go up to 6.5 sigma here. So this you see from the plot here. Standard model is just again 0, 0, but you see here that the red band from MW is pushing you this ellipse up. So you would like to have a positive effect in the T parameter here, which just tells you you want to reduce the splitting between W and Z mass. There's also 2T sigma tension in Z to BB bar. I think that's interesting in light of the B anomaly. Because if you have new physics in B to S mu mu and B to C tau nu, why not in Z to BB bar? And of course, it could also be otherwise related to lepton-flavor universality violation because T-2 of the muon measures electroweak symmetry breaking. So this is also a possible combination here. Okay, so this brings me to the summary of the first part of the talk, namely
Andreas,
the anomalies we have.
I have a question.
Yes?
This is about the earlier slide.
Sorry?
I have a question about the earlier slide, slide 21. So,
can you speak a little bit louder?
Yeah. I have a question about the earlier slide, slide 21. Yeah. So, was this tension there at all before the CDF announcement?
Yes, before the CDF announcement, it was 1.8 sigma.
Okay. Thanks.
So again, my very personal opinion, I think the central value of CDF is too high and the error might be a bit too small, but as it goes in the same direction as before, and there are some nice possible explanations here, I think it's an interesting anomaly.
Thanks.
Okay, so now I put it into three classes, this hint. First of all, lepton-flavor universality violation. So this is called Piper angle anomaly, G-2, B to S mu mu, B to C tau nu, and also B to C mu nu, and this measurement of proton-proton to E plus E minus. In addition, we have the electroweak observables, W mass, Z to BB bar, and then what I couldn't go into detail here, since Morion, more and more small anomalies in direct searches pop up. So there are some hints for diphotons around 96, 125, 680 GeV, tau pairs at 96 GeV or 1 TeV, 4Bs, BB bar tau tau at 1 TeV. So this is not the main focus of the talk, but I think it's interesting to keep in mind that also anomalies at direct searches are popping up now. Okay, this brings me to the end of the first part of the talk. How much time do I have left?
Namit?
How much time? 20 minutes, 25?
25 minutes?
20, yeah, that's more than enough. That's more than enough. So please continue asking questions.
Okay, since you
Any questions?
said that, can you hear me?
Yes.
Yeah. So this is G-2 of the muon where we have 4.2 sigma. So again, my naivety here. So I thought there was one group was claiming that there is no tension, like the European group, I forget. So what is your?
Yeah, BMW.
Yes. So how do you
they definitely can't claim there's no tension at all. They can say they significantly reduce the tension in G-2, but then they have a nearly 4 sigma tension in their result versus the extraction of hadronic vacuum polarization from E plus E minus to hadron.
I see. So they solve this tension, but they show tension elsewhere. I see. Oh, okay.
Exactly. So they solve this tension, but they create a tension somewhere else.
All right.
The problem is there are some attempts to do it, but a new physics in the plus and minus to hadrons is nearly impossible.
I see.
And the new W mass measurement would also, and if you take the BMW result, it also increases the tensions in the global electroweak fit and also drives the W mass in the opposite direction than the CDF measurement.
That comes from the delta alpha, right? I mean, the sort of relationship between the running of the delta alpha electromagnetic.
Yes, exactly.
Yeah.
So
okay.
hadronic vacuum polarization enters the running of the fine structure constant, and this, if you take BMW here, this slightly increases the tension within the electroweak fit.
Okay.
Okay, thanks a lot for the questions. So let me continue to the new physics explanations of the anomalies. So RD star, simple and easy at the same time. You need, it's tree level in the standard model, you need tree level new physics to get the 10% effect you need. It's a charge current, so there are only 3 possibilities how you can get such a charge current with new physics. Charge takes W prime leptoquark. Charge 6 W prime don't work very well because of LHC searches or also Q-square distributions. So in principle, you are left with leptoquarks. They are constrained from tau searches, but it's still working. So an explanation is not easy, but you can do it with leptoquarks. BS mu, on the other hand, it's quite easy to find an explanation, and there are probably now something like 100 articles dealing with that prime explanations. Here, what you should keep in mind is that what you need here is this coupling to BS and a coupling to muon. The BS coupling must be much smaller than the muon coupling because you can double the left-handed side and then you get BS mixing, which gives strong constraints. Also, a Z prime can be produced in the S channel at the LHC, so it should be either quite heavy. In this case, you would increase the tensions with BS mixing, or you avoid first generation quark coupling. Then it's compatible with LHC searches. There's quite a number of loop contributions. So BS mu is the loop process in the standard model, so you can also account for it at the loop level in new physics. That new scalars and fermions in loop, 2 doublet model, R2 leptoquarks, Z prime with top coupling, or maybe also a combination of loop with tree effects. We don't know yet. We need more data. Leptoquarks again work very nicely, maybe too nicely. They give a tree level effect here. No, everything else is loop suppressed, so it's hard to determine if leptoquarks are the origin here, but they definitely work very nicely. T-2, of course, it was always considered to be the smoking gun of the MSSM, so tension beta enhanced lepton loops. It could be a light scalar, maybe with enhanced muon coupling, a Z prime, either around 0.1 GeV or with tau mu couplings, new scalars and fermions. This is just a generalization of the MSSM in some sense. And what works again very nicely are leptoquarks. They have an top over a mu enhanced effect, so 1,600, which is huge. Now, square root 1,600 tells you you can even get have 10 TeV leptoquarks, which can explain G-2. And the way it works is this diagram. So you couple a left-handed muon to a top quark, you do the chirality flip with the top quark mass, and then you get out the right-handed muon. And here the interesting thing is you also get chirally enhanced effects in H2 mu mu and in Z2 mu mu. And for the latter one, it's quite nice because there are only 2 scalar leptoquarks which can explain G-2 of the muon. SU2 singlet phi 1, SU2 doublet phi 2. The singlet predicts a constructive effect in H2 mu mu. The doublet predicts a destructive effect in H2 mu mu. So if you measure this very precisely, you can already indirectly exclude one of the 2 leptoquark possibilities. Caviber angle anomaly. So as I said, we need new physics either in beta decay or in the determination of the Fermi constant, or in both of them at the same time. Now, you can have a direct contribution to beta decays. This you can do with leptoquarks or W prime. You can have an indirect effect in muon decay via a modified W mu coupling. This could be W prime mixing or vector-like leptons. You can have a direct new physics contribution to muon decay. This could be a Z prime or singly charged scalar, or you could have a modified quark W coupling. This could be vector-like quarks. So what works quite nicely are these modified muon couplings, because in that way you can also improve the global electroweak fit. And this is an example with vector-like leptons, singlet, so quantum numbers of the right-handed neutrino, a triplet, so quantum a triplet with hypercharge 1. And then you see you can even do 5 sigma better than the standard model, because you don't only explain the Cabibbo angular anomaly, but also improve on the global electroweak fit. Non-resonant dielectrons, here what works nicely is purely left-handed new physics with order 1 couplings at the 10 TeV scale. So here you see this is this Wilson coefficient. It has only left-handed quarks and left-handed leptons of the first generation. And I took here a triplet structure, so it contains a neutral and a charge card. This is not important yet, but as you see here, this solid line gives the best fit. And the solid line is just order 1 coupling for 10 TeV new physics. So I would say that's not completely unnatural.
Sorry, can you go back?
Delta AFB?
Sorry, can I ask one question? One slide
Yes.
before this. One slide before this. Yeah, here, if you know, since you said about this, this is electroweak fit and Cabibbo angle anomaly. If you use now the newer value of CDF, will there be a change in this?
Yes, but you cannot fully account for the W mass via modified gauge boson coupling to leptons.
Okay.
You need, in addition, something in the operator which directly splits you the W from the Z mass.
Okay. So
there's
the
impact,
short
but a full
answer is that
explanation of the
this
W mass
plot is not going to change too much.
It's not going to change too much, no.
Okay, that's the answer. Okay, thank you.
Thanks for the question. Okay, then delta AFB, I think this you already all explained. So here you need a scalar leptoquark because you need a tensor operator. Without a tensor operator, you cannot get a good fit. And importantly, a tensor operator at the dimension 6 level, at 3 level, can only be generated by a scalar leptoquark. There is no other possibility. So this means if delta AFB is confirmed, you indirectly prove the existence of a scalar leptoquark. W mass, here are many possibilities. Loop effects with sizable Higgs coupling. So again, new scalars and fermions in loop with a large Higgs coupling. Something that works easily is Z prime mixing. If the Z prime is an SE2 singlet, you can have SE2 triplet scalar, which gets a web. Or again, you can do it with loop effects via leptoquarks. Here, an example with new fermions in the loop, namely new vector-like quarks. And what we want to show here is this is the coupling to charms, this is the coupling to top quarks. And now what you see here is that you can get sizable branching ratios for top to Z charm. So the W mass measurement, this is this boomerang here. This boomerang prefers a really sizable coupling of the vector-like quark to tops. And now if you have in addition a coupling of the vector-like quark to charm quarks, not even that large, then you predict a sizable range for top to Z charm without violating bounds from B2SLL and so on. Okay, this brings me to the end of the second part. So I have some slides on spontaneous explanations left, but I'm also very happy to answer first some questions.
Okay, so one question maybe I can ask since you are allowing that. So this is for the where you said yes, G-2. We said you can have SUSY there, then leptoquark. But I was thinking even for the FCNC, the anomaly in the FCNC, B2 SMU or because I thought even the R parity violating SUSY, I thought there was a paper by Sony and some other, I forget that. But there was also the claim is that you can also explain with the RPV. So, I mean, the question is, can we, I mean, I know in leptoquark also can be part of the R parity violating SUSY or something that I thought yeah. So how do we really say that it is not SUSY, right? Like this, let's say.
I said MSSM, and for me, MSSM is the minimal supersymmetric standard model with R parity conservation.
Okay.
So
sorry,
R parity violating MSSM, I would subsume as leptoquarks. But
right, that is what I was.
Leptoquark, yes, but the leptoquarks in the R parity violating MSSM don't have the right quantum numbers to give this chirally enhanced effect in G-2. So still in the R parity violating MSSM, you need to explain it with the usual SUSY loops. You can't do it with the leptoquark loop.
I see.
So the point is that as you have the only possible leptoquarks in the R parity violating MSSM are of course the squarks, and they don't have. I'm sorry, and they have the quantum numbers of the of this SU2 singlet, but R parity violating SUSY doesn't allow for both couplings to left and right-handed muons. This is why you can't do it. Okay, thanks. Any more questions? Okay, then let me spend some few minutes on simultaneous explanations. Don't get frustrated if you don't understand everything. That's just to highlight a little bit what one could do here. So what works very nicely is the Party-Salam vector leptoquark, which is the SU2 singlet. It gives a left-handed current in BS mu, left-handed current in RD star. It nicely explains both of them without violating B2SU nu. It has the correct quantum numbers to not give rise to proton decay at any perturbative order, and it's contained within the Party-Salam model. This is why it's called Party-Salam leptoquark. So,
Andreas, sorry.
In the Party-Salam model, you need.
Oh, okay. It seems that for some of
Yes,
us, the
please.
slide is stuck at leptoquark in MU. Christina is also seeing the same thing. I am also seeing the same thing. But Rohini says it's okay. Okay.
We see page number 27, Namit, just to tell. I see page number 27.
Leptoquarks in MU, right?
Yes, that's what I see, page number 27.
It should be vector leptoquark SU2 singlet.
No, it's not.
Yeah. So we see 27.
It's not.
Can we? Yeah. Maybe you can restart. I mean, sorry, you can.
Yeah, you can just flip the slides up and down, and that should reset it.
Yes, thanks a lot for letting me know. Can you see it now?
No.
No.
I'm seeing a blank screen.
No, we see a blank screen.
Interesting.
Are you sharing the entire screen, Andreas, or just the PDF file, whatever you have?
I didn't change anything. That's a strange thing. It should still work. Can you see it now?
No.
No. Blank.
Maybe log in and log out and log
Yeah.
in. That works.
Yeah, I think he has logged out and probably rejoin.
Anyway, he was having strange issue. We'll take a photo. Andreas upside down.
Yeah, that is very interesting.
Can you see it now?
Yes.
Yeah, everything fine.
Yes.
Yes.
Vector lab to quark SU2 singlet?
Yes.
Yeah,
yes.
we do.
Yes.
We do.
Okay, great, good. Then that's solved. Okay, so what I was saying is that this vector lab to quark SU2 singlet, also called the party-salam lab to quark, because it's contained within the party-salam gauge group, which is SU4 cross SU2 left cross SU2 right, where SU4 is contains as a four-plet the three colors and lepton number. This is the name of the original paper, lepton number as a fourth color. So this works very nicely. Left-handed effect in B2S mu, left-handed varactor current in RD star. Importantly, no tree-level effect in BS nu, which gives otherwise stringent constraint for B2K and K star nu. No proton decay at a renormalizable order. But it's difficult to construct such a V-complete model because it has a massive vector boson. So you need something like a Higgs mechanism or composite extra-dimensional. And you also need to avoid K to mu E, which is very important. If you're interested, ask me. I think I have a backup slide on this. And what I really like about it is it gives a perfect agreement to data via a correlated effect in RD star, and B2S mu. So Rx is RD or RD star over its standard model value. The blue band is what is preferred. And the yellow egg, this is B2S LL. And B2S LL, you see, nicely overlaps. And the reason why it is an egg and not a band is the following. So here you have a tree-level effect in C9 equals minus C10. This, you get a tree level. And then RD star, this is B to C tau nu, via SC2 invariance gives B to S tau tau. Then you close the tau loop, attach an off-shell photon and a lepton pair, and you get C9 universal. And then you are back to this B2SLL scenario I showed you at the beginning. And then it turns out that RD star really generates the C9 universal you want to have to get a very good fit. And then in combination with the tree-level effect in muons, you get this scenario which fits best. And as I said, it's important that this yellow egg overlaps with the blue band. Okay, another thing is a model that can explain Cabibbo angle anomaly, tau to mu nu, Z to BB bar, and B to S mu. Here on the left, this is just the standard model, but extended with a mu minus a tau gauge symmetry. Now, to this, we add two pairs of vector-like quarks, SU2 doublets and SU2 singlets, a singly charged scalar, and a singlet scalar, only charged under L mu minus L tau. Now, what is happening is this singlet scalar, the VEF, gives a mass to the Z prime. The vector-like quarks only also couple to S, and so it's natural that the vector-like quarks and the Z prime have the same mass scale. And in addition, the quantum numbers, like we have them, will enforce you that you get B, that you can only construct the loop that way, so you get a Z prime penguin giving rise to B to SLL. You get a modified Z to BB bar coupling, explaining the old lab anomaly, but it also gives rise to a Z to BS coupling, which helps you further explain B2S mu. And now if you put everything together, it looks like this. You have the vector-like quarks. They explain via the mixing with the standard model quarks set to BB bar. Then the set prime via box diagram explains tau to mu nu. The singly charged scalar at 3 level gives a modification of the Fermi constant. And all together via this loop diagram here gives rise to B2S mu mu. And all of it nicely works for something like 1.5 TeV. You can, even in a model independent way, explain the Capipper angle anomaly and non-resonant dileptons at the same time. So here you take this operator, which only couples left-handed quarks and left-handed leptons of the first generation. And as I said, it has a SU2 triplet structure. So it contains a neutral current. This gives you Q bar to E plus E minus. And a charge current. This gives you UDE nu. UDE nu is just beta decays. So this explains the Capipper angle anomaly. And now on the left here, you see the delta chi-squared. So how much you improve on the chi-squared compared to the standard model. And then you see at the same point where you explain green, the Capipper angle anomaly, you explain red, the CMS measurement. And this is not excluded by Atlas. And it's even compatible with R-Pi. Finally, BSLL W mass Z prime mixing. So here, Z prime mixing, if the Z prime is singlet, perfectly explains the W mass measurement. Now, Z prime mixing, in that way, the Z inherits the BS couplings of the Z prime in case the Z prime explains B2SLL. Then you get an effect in C10 and you change the global B2SLL fit. And now, this you see here on the right-handed side. So on the bottom, this is the new coupling of the Z prime, and Xi is the Z prime mixing angle. Now, here, red is the electroweak fit. Now you see, because of the new W mass measurement, the electroweak fit prefers a non-zero mixing angle. And also B2SLL prefers a non-zero mixing angle because it doesn't want to have C9 only, but also a small C10 contribution is welcome. And then here, this perfectly overlaps. So both the electroweak fit and B2SLL prefer a non-zero mixing angle. Okay, this brings me to the conclusion. So you have seen all these anomalies. I didn't talk much about the LHC anomalies, but you see here, they really range over 1, 2, 3, 4, 5 orders of magnitude. They contain hints for lepton flaviluminosity violation, deviations in electroweak positions observables, and now also some hints for direct euphysis. So I think this is promising in the sense that the standard model seems to crumble. After 5 decades of confirmation, we finally seem to get first hints that it's not the end of the story. And if it's not the end of the story, we need to extend the standard model by new particles. For example, leptoquarks, vector-like fermions, new scalar, a Z prime boson, a W prime boson, and then this is a diagram I constructed how these different anomalies point towards different extensions of the standard model. So I hope I was at least able to convince you that we are living in an exciting time and that for the PhD students, it's worth doing research in this area. Thanks a lot for the attention.
Thanks a lot, Andreas, for a very interesting talk. We have time for some few questions.
Yes, I have one, if I may.
Please, Christina.
So thank you very much, Andreas. An excellent talk. Now, I would like to ask a question on a slightly different angle. So I was wondering if you could give us some insight of what you think the correlations might be, or the implications, in fact, possible implications on the kaon sector.
Let me see if I have a backup slide on this. So this U1 lepto quark is definitely nice for kaon physics because via loop effects you also generate k to pi nu. I hope I have a backup slide on it, but I'm not 100% certain. No. No, I'm sorry, I don't have the backup slide, but it's similar to B to K star nu. So the vector lepto quark generates at tree level B to S tau tau and also B to C tau nu. Now, via box diagrams, you get B to S neutrino antineutrino. But if you don't only explain B to C tau nu, so RD star, but you also want to take into account B to tau nu, a B to U transition, and you combine both, then you get very interesting predictions for K to pi nu. Another angle would.
May I ask, charge neutral or both?
Both.
Both, okay. And that's the only rare case where you see a leptoquark effect? Because is there, for example, any other leptoquark effects in other rare kaon decays?
Of course, there are also other leptoquark effects in rare kaon decays. You can get an effect in RK. Okay, that's not rare, but you can get an effect in RK. Then it's not directly the leptoquark which explains the B anomalies, but it's still interesting. But for example, if you explain this proton-proton to E plus E minus measurement with a lepton quark, you expect an effect in K to mu nu over K to E nu. Then
okay.
For the Capippo angle anomaly, K to pi L nu is very important. So the determination of VUS from K to pi L nu is very, very important for the Capippo angle anomaly.
Yeah.
And with K to pi LL, you can, of course, test lepton flavor universality like you test with RK.
Okay. Do you have any particular papers on this that I can look at?
Yes, if you send me an email later, I will reply and send you some links.
Thank you very much.
Thanks a lot for the question.
Jim?
Yeah, I had a question just with all these various models that may explain these anomalies. If you go back to your opening slides and you talked about the problems of the standard model where you had dark matter and CP violation and neutrino mass, which of these also provide explanations of those phenomena as well? Or do we have to look for further things or which have the best connections to solving those cosmological issues, I guess is the question.
I mean, solving these cosmological issues is normally just extending the models. There's no direct connection. The closest connection I would see at the moment is generating neutrino masses because they are linked to lepton flavor universality violation like the anomaly.
Okay.
But otherwise, I mean, leptoquarks can be a portal to dark matter. Z prime can be a portal to dark matter, but none of the particles I discussed can by themselves be dark matter.
I understand. So also,
and I mean, you also need to do some research in the future.
No, that's good for our younger participants for sure.
Yeah.
Yeah, I also have one announcement now. I'm speaking. Unfortunately, Chris Polly, our last speaker, has had a family emergency, and he's currently at the hospital dealing with a relative. So he will not be able to give the final talk. But what that does mean is we have plenty of time to ask Andreas questions if he can stay with us for a little longer. So please feel free to ask as many questions as you can. And I apologize, the last talk has had to be cancelled, but it's for good reason.
Gagan?
Okay. Yeah. Right. And yes, so you showed just one slide before that we should definitely go for FCC HH, but clearly,
and FCC.
Yeah, of course.
Okay,
We already had a very nice. Right, go on.
Yeah, this is my backup slide for FCCEE, which also
Absolutely.
applies to CPT.
Right. No, we had also a wonderful talk in the morning about FCCEE. Right. So, but of course that will take some time and efforts to get the funding agency on board. And of course, I don't want to get that far. So the point is in the immediate term or near term, what will be, of course, like B2 S-mu anomaly. Of course, we would like to have confirmation of the LHCb part, let's say Belle II or but that of course the rate Belle II super Kekman is more from the accelerator side, so that's taking time. On the other hand, what would you recommend? I mean, what would be your immediate suggestion for us experimentalists working both at let's say FLAVOURS side or even Atlas CMS side? That I thought last time we had a talk from you at CKM Heidelberg, if I remember correctly. So you were saying about this tau measurement at LHC. So what is that you tell that we should really focus on if we could say, like in a priority basis, keeping in mind that it will take some time for Belle to have a data set where we can have a competitive measurement like LSB. And so, yeah, that will take some time. Of course, if CMS can do, but obviously is challenging. I mean, CMS or Atlas, it is challenging.
Yeah.
From various
so what I know is that CMS is at the moment unblinding B sub S to mu and RK. We should get some results on this quite soon from CMS. Then CMS should also provide very soon RD star. Sorry, I think. Can you still hear me?
Yeah, we hear you. Yes.
I heard some feedback. Sorry. Yeah. Then so from CMS there will come something quite soon. Then I was told that Atlas will release an update of proton-proton to E plus E minus at CEPC. So also something quite soon here. Then I know this is not too short term, but I think you as Belle should definitely push for your polarization upgrade. You can do very great physics with this polarization upgrade, and the effort or the costs are quite small compared to what you could achieve there. You can do better on set to BB bar than Lab did. You can measure the anomalous magnetic moment of the tau at a competitive, at a precision which is relevant for new physics. And I think that's the only way you could do it. So the polarization upgrade of Belle, I would really like to promote this.
Right, but that clearly I can say with some confidence that right now the priority is more on the getting the machine to deliver the data at the, sort of close to the desired. So more on the flavor anomaly or that. Yeah. But clearly
what you could.
What you are, yes.
Sorry, there's always a slight delay. I'm sorry.
No, go on. Sorry, you are saying. I'm done. Yeah.
So what you could do directly is to do with the old Belle data RK inclusive. So B to XS mu over B to XS EE. You have the data. The analysis was already presented something like 12 years ago at a conference. You found 0.3 plus minus 0.3. So it goes perfectly in the right direction, but the analysis was never published. But you have the data on tape. You would just need to finish this analysis. This you could do immediately.
Okay, so this is marked for a PhD student. Okay, great.
Can I just quickly comment on that? I believe someone is working on a Belle plus Belle II analysis of this type, Sato-san. So I think it will happen, but it's a tricky analysis. So it will take a little time. But someone is now working on this again. You'll be pleased to hear.
I think I still have the slides if you want to see where this result of Belle was presented 12 years ago. So
I can know what happened. Someone graduated and then things ground to a halt. So, but yeah, it is being worked on again. I saw a talk about it a couple of weeks ago. So it's been restarted a little while ago.
Any more questions? You could raise hand or.
Yeah, no, so I can go on since no one is asking. So this is about the delta. You said, which delta? There are so many delta. That where you are showing that the old, right. There was a 4 sigma discrepancy. So I think it was slide number 13 or 18. I'm forgetting that. Yeah, I actually should check that paper. Yes, this one, right? The delta AP, right? So if we start from this, and then what will be the prediction for any other variable, any other observable that one can look at on this? Because this we can even do in Belle II, like let's say, although whatever small data set Belle II has collected, this kind of thing will be interesting. Probably I should check about the feasibility. I mean, in terms of the statistical sensitivity, right? So, do you think that independent cross-check from Belle II will be good here?
Yeah, definitely. And what you can also look at is this delta FL and delta FL tilde. This already gives important constraints. And of course, you should look at B to D star mu nu versus B to D star E nu, also the total branching ratio. So you can improve on this orange boomerang here. This is the total rate of muons versus the total rate of electrons. And you can improve on this green and dark red regions, which come from delta FL and delta LF tilde.
I see. Okay, very interesting.
Does this answer your question, or?
Yes, it does. It does.
Any more questions? Okay, I don't see anybody asking anything. So thank you, Andreas, for a very interesting and a lot of discussion happened during the talk. Thank you very much for accepting our invitation and joining today. Jim, over to you.
Thanks a lot for all the great questions. It was really a pleasure today. Thanks a lot.